In this video, we continue with the computer science A-level curriculum, taking a look at the A-star algorithm. And just like every other video, we take a look at the learning targets first. So candidates should be able to show an understanding of how graphs can be used to aid artificial intelligence. We need to know the purpose and structure of a graph. In this video, we're going to be using the A-star algorithm to perform searches on a graph. In the last video, we used Dijkstra's algorithm. And just a reminder, candidates will not be required to write algorithms to set up, access, or to even perform a search on graphs. So let's start by talking about some of the drawbacks to Dijkstra's algorithm. So we looked at Dijkstra's algorithm in the last video. It checks for the shortest path between two nodes. The downside to this is you may have to work away from your destination because it pays no attention to direction. When graphs become larger or even more complex, this becomes very time consuming. And this is where the A-star algorithm comes into play. So the A-star algorithm is based on Dijkstra's algorithm. Well, if it's based on Dijkstra's algorithm, what is the difference? Well, it adds what is known as a heuristic value represented by h. Now, a heuristic value is an intelligent guess on how far we need to go to reach our destination using an efficient path. So today we're going to take a look at a scenario. Now I just want to say the scenario comes from the Computer Science 9618 AS and A-level book. They have a wonderful example, and I believe in giving credit where credit is due, so we're going to be using their example today. Now, before we work the scenario, there are some vocab terms we need to become familiar with to be successful. So let's take a look at our scenario first. So here's our scenario. They tell us to find the shortest path for the figure given below. So they give us a graph here to work with. You're allowed to move up, okay? We can move down, we can move left, right, and we can move diagonal. Perfect. Make note of the legend. Okay, so we have our starting point, we have our ending point, or our finishing point they call it, which is the ending point. We are allowed to move inside the white squares. We are blocked by the gray squares. So as long as we make note of that, we're good to go. So now each part of this graph is a node, and each node has 4 values. We said there's some vocab, so here comes the vocab. The first one is the heuristic value represented by h, the movement cost, which is represented by g, the sum of the g value and the h value, so the heuristic plus the movement cost, that's going to be represented by f, and then the previous node of the path represented by n. So the distance between two nodes is the movement cost, which is also known as weight. But the first step is to find the h value. We cannot find the distance until we find the h value. Now, to find the h value, you use what is known as the Manhattan method. This method means you count the distance between the starting node and the final node. Now, you can choose to ignore the block moves or to move around the block moves. The distance will be the same. So we're going to take a look and see how this works, counting to the square going through the block moves and again going around the blocked moves. So here we go. To get to our final or finishing point, let's count the distance. 1, 2, 3, 4, 5, 6, 7. Now I need to go down. 8, 9, 10, 11, 12. So that's going through the blocked moves. But what if I don't go through the blocked moves? Now, when you're counting the distance, we are not looking for the shortest path. So you're going to go up, down, left, and right. You are not going to go diagonal. So let's go around the gray squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's try another way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. As long as I'm working towards my goal, I'm always going to count the distance correctly. So we counted the distance and we see that it's 12 squares. Well, what about that orange line? Let's count the distance. 1, 2, 3, 4, 5, 6, 7, 8. Let's go around the gray squares. 1, 2, 3, 4, 5, 6, 7, 8. And I can also go down because down will still bring me towards my goal because I know my finishing point is at the bottom. 1, 2, 3, 4, 5, 6, 7, 8. So we can count the distance between that too. We see the distance here is 8 squares. So what do I count? Do we count the starting point? Do we count the orange line? You must calculate the value from every white square to our ending square, which will give us our heuristic value. So give this a try using graph paper to calculate the H value. I left a link in the description where you can print graph paper if you would like. It'll take you directly there and you can print any graph paper you would like. But go ahead, pause the video, and all you're going to do inside these white squares is write the heuristic or the H value. Go ahead and pause, and then I'll show you what you should have. Okay, so you went ahead and calculated your H values, and this is what you should have. If I pick this square right here, which is 8, 1, 2, 3, 4, 5, 6, 7, 8, going through the blocked moves. If I do it this time going around, 1, 2, 3, 4, 5, 6, 7, 8, I still get that same value. Now this 6 that we're talking about here, notice that it does not loop around, and that's because we should always be moving towards our goal, so make sure you keep that in mind. But after we count all of the H values up, we get this. Now we need to talk about the movement cost. So now that we have all the H values, we need to find the movement cost represented by G. Now to make the calculation a little more simpler, we're going to use a right triangle, and you may be saying, why in the world are we using a right triangle? Where in the world did that come from? Because we can move up, we can move down, we can move left, right, and diagonal. So let's take a look at these values and understand what in the world I'm talking about. So on a right triangle, side A, I can move down. I can also move up. That gives me a value of 10. Moving left to right or right to left, that gives me a value of 10. Diagonal will give me a value of 14. And if you remember the formula for solving a right triangle, the hypotenuse of a right triangle is a squared plus b squared equals c squared. A squared plus b squared equals c squared. You take the square root, it comes out to 14 point something. So we just rounded it down to 14. So if I move down, I can see that has a value of 10. That corresponds to the left side or the A value of the right triangle. If I move left to right, that gives me a movement cost of 10 based on the triangle. But if I move diagonal in any direction, that will give me 14. Now notice in this, the hypotenuse is moving from the upper left to the upper, the upper left to the bottom right. But it is also the same distance if I move from the upper right to the bottom left and mirror this triangle. So we can now solve for F. Now that we can figure out G, we've already figured out H, we can solve for F. Now the F value is the sum of the G value and the H value. So let's take a look at our starting vertex, which was 1, 1. We must also look at the surrounding squares, which are 1, 2, 2, 1, and 2, 2. These dashes are temporary. They are temporary because we're looking based on where we currently are. So let's take a look at the G values. Well, I can move down. What is the movement cost when I'm moving down? It has a movement cost of 10. What about when I move to the right? That has a movement cost of 10 based on our triangle. When I move down towards the right, that has a movement cost of 14. So we look at the H values. Now what we've done here, this is not a new graph. We've zoomed in on the upper left part of the graph, looking at the first 9 squares, the first 3 by 3 squares. So now all we need to do is we need to add some values. So square 1, 2, that is 10, plus the H value, which is 11, that gives us 21. Square 2, 1, 10, plus 11, that gives us 21. And then square 2, 2, which is our G, 14 plus H, which is 10, which is 24. So now we compare those values. We look for the smallest F value. This tells us where to move to next. So square 1, 2 gives us a value of 21. 2, 1 gives us a value of 21. And square 2, 2 gives us a value of 24. 21 is smaller than 24, so this tells us where to go next. But wait, there are 2 values that are 21. So what do we do? Well, they are the possible directions we can go. So we're going to move to 1, 2, or we can move to 2, 1. We're going to move to 2, 1 as our next step. And you may be saying, well, what about 1, 2? Don't worry, we're going to come back to it shortly. So we need to find the sum of G and H values based on where we currently are. We said we're moving to 2, 1. This is where we are. I can move right, gives me a movement cost of 10. I can move down, which gives me a movement cost of 10. I can move diagonally to the right, which gives me a movement cost of 14. Down and to the left, with a movement cost of 14 down to the right with a movement cost of 14. Now that I have those, I tack that on to my existing h values. So square 3, 1, 10 plus 10. Then I do square 1, 2, 14 plus 11, it gives me 25. 10 plus 10, which is 20, 14 plus 9, which is 23. This 8 hanging out here, we do not do anything with because it is not adjacent to where we currently are. So now we compare those values. So 20 is our smallest number, and again, we have two choices because we have square 3, 1, and 2, 2. We're going to be taking the 3, 1 route. We're going to continue finding the f values. Do not worry, we're going to come back to the one that we are ignoring, square 2, 2. So then again, we do the same thing. We find the sum of g and h values. Here I am. I can move diagonally to the left, I can move down, or I can move diagonally to the right. So square 2, 2, 14 plus 10. 14 plus 10 gives me 24. 10 plus 9, right here, gives me 19. And then 14 plus 8 is 22. 19 is the smallest. So it's on the 3, 2 we moved. Now, by this point, you should be looking for a pattern in the best case scenario because it can take a long time to work all those values. GPS, Google Maps, the spread of diseases, even IP routing are example of items that make use of the A-star algorithm. Now, computers are faster than we are at doing calculations. If we work the rest of this out on paper, God, we're going to be here a while. But computers can do it very quickly. Now, one option we have for finding the shortest route is to continue or to look for a pattern. Now we're currently at vertex 3, 2. So now what I need to do is I need to pause here and I need to ask myself, okay, what are the paths to get here and what are those values? Remember those values we said we would be going back to? Now it's time to go back to those. So to get to node 3, 2 from our starting node, there are 3 possible paths. I can go down 1 and 2 to the left. I can go right 2 and down 1, or we can go diagonal towards the right and then 1 to the right. So I can go down 1, 2 to the right, not 2 to the left. It's not 2 to the left, I'm sorry. Down 1, 2 to the right. I can go to the right 2 and down 1, or I can move diagonally down and then right 1. Well, how do I know which is the best path to get to vertex 3, 2? Because I've worked out some values here and I'm looking for that pattern. Well, I add up all those values. So route 1, when I go over 2 and down 1, I have 21, I have 20, and 19. Those are the values that we looked at just a few moments ago. When I look at route 2, I go ahead and I take a look at the f values, which was 24 plus 19. That gives me a value of 43. Route 3, I look at the values, the f values. So 21 plus 20 plus 19 gives me 60. So what does that data show us? It shows us when possible, we should move diagonally down and right when possible. When not possible, we should move to the right or towards our end point. So when we do, we find our shortest path. And our shortest path, looking at this graph, is 1, 1 to 2, 2 to 3, 3, then on to 4, 4, 5, 4, 6, 4, 7, 5, and then 8, 6. Now, when we get here, we could also move diagonally up. However, if we had moved here, then the route to square 5, 4 would be 5 squares. By choosing 3, 3, it's only 4 squares. So, if we moved here to get to 5, 4, we'd have to go 1, 2, 3, 4, where if we go from here, 1, 2. So that is where we can do that. So if you start there, 1, 2 to get to 5, 4, or if we go up 1, 2, 3, 4, it's an extra square there. So I hope you found this video helpful. If you have any questions, please post a comment below. And if you did find this helpful, please give a thumbs up and consider subscribing to help the channel grow. And we'll see you guys in the next video.